Alright, so we're going to have a look at another example of an ordinary differential equation. So this time we're going to have a look at another first order separable, but this time it's going to have an initial condition. So our question here is going to be dy dt is equal to ty plus 3t over t squared plus 1 with the initial condition y of 2 is equal to 2. Now essentially we need to solve this using the initial value condition as well. So we first need to find a general solution, then this initial value condition y of 2 equals 2 will help us find a specific solution. So we're going to do this pretty much the same way we've done most of this stuff. Most of the first order separables, we're going to move all of the y's to one side with the dy, move all the t's to one side with the dt, and then integrate. So we get dy dt, we can factor t out of the numerator. So t times y plus 3 divided by t squared plus 1. So this gives us 1 on y plus 3 dy, divide both sides by y plus 3, is equal to t on t squared plus 1 dt. Now integrate both of these. 1 on y plus 3, this will be the natural log of y plus 3. So this becomes natural log of the absolute value of y plus 3 plus a constant, which we'll call c. T on t squared plus 1, this is also a natural log. It's going to be the natural log of the absolute value of t squared plus 1 plus a constant, which I'll call d. Now we need a number in front of this as well. If we differentiated log of t squared plus 1, we would find that the answer was 2t on t squared plus 1. So we actually need a 1/2 coefficient in front of this. And we're going to move all of the numbers, the c and the d, to one side. So we'll minus c from both sides. There's a new constant over here, we'll call it e. So now we have the natural log, the absolute value of y plus 3 is equal to 1/2 times the natural log of t squared plus 1, all plus a constant e. You could just call the constant c, d, and then call this constant c. I'm just calling it e out of habit. You don't have to do this though. So now we need to solve this for y. So put these both under a base of e. E to the natural log of the absolute of y plus 3 is equal to e to the 1/2 times the natural log of t squared plus 1 plus e. These are all in the power. E to the logs cancel. So we get e to the log of y plus 3. This side becomes y plus 3. The other side is a little more complicated than that. This becomes e to the e, because these are added. Index law would tell us that e to the 1/2 times log of t squared plus 1 times e to the e is e to the sum of those two terms, times e to the natural log of t squared plus 1 all to the half. Because a half times the natural log, the other index law, the power index law, a power to a power, you multiply them. Now the e to the log in these brackets, so this becomes y plus 3 is equal to e to the e. Now remember, e was a constant, so e to the e is just a new constant, we'll call it f, times e to the natural log. These now cancel, so this becomes t squared plus 1 to the half. Okay, so now we've got this solution, and we're assuming when we're doing this that the t squared plus 1 and the y plus 3, when they went into the absolute value of the log, that they were essentially made positive by the log, but now we've got rid of the logs, that's no longer a concern. They could have been negative because it was the absolute value and the natural log would have made them positive. Now they can just go back to being positive or negative. So now we need to minus 3 from both sides. So we get our general solution, y as a function of t, is some constant f times t squared plus 1 to the half, all minus 3. This is a general solution. This is the first part of the answer. It's a general solution because it has an f, it has a number in it, a coefficient f that we don't actually know. And this f will vary depending on this initial condition over here. So now we need to let t equal 2 and let y equal 2. When we plug these in, everything will resolve and we'll just have an f. F will be the only unknown thing. We can solve for the f. That will be the specific solution. So now we get 2 is equal to f times 2 squared is 4 plus 1 to the 1/2 minus 3. So if we add 3 to both sides, we get 5 is equal to f times the square root of 5. Divide both sides by the square root of 5. This tells us that f is the square root of 5. And so this means this was our general solution. Our specific solution, this is going to be y equals the square root of 5 times t squared plus 1 to the half minus 3. And so we first found the general solution. We then found the specific solution by using the initial condition. So this is most first order separables which have an initial condition work approximately in this fashion. You solve as normal, as if it didn't have an initial condition, then you use the initial condition in order to find values, find typically coefficients in your answer which were previously unknown. Now again, this is a common stopping point for many students. Many students will say, well, I'm done, I don't need to do any more. This is a poor idea because you know the y function, you may as well try and check. You can try and do this. It's a little messy because we have to have a really horrible derivative, but you should be doing this. Right? This is university level work, not school level work. At school level work, you can just sort of go through it, present your answer. Some students choose to check, some students don't. Often students don't need to. So the teachers are perfectly happy for them to just go through it, try and provide the answer, and then they move to the next class regardless. You know, you can get 100% on an exam in any course without checking, but when you get to university, it's much more important that you start checking wherever possible, especially for assignments, right? Because if you have home assignments that you're doing on differential equations for finance or engineering or maths, physics or whatever, they need to be right? There's a lot of marks put on you actually doing equations properly and knowing that you've done them properly. So you have to check them. So if this is y, we need to find the derivative. So dy dt is going to be equal to, well, this is a chain rule. The minus 3 will go away because it's just a number. So we're going to have 1/2 times root 5 times t squared plus 1 to the power of minus 1/2, all multiplied by the derivative of the inside, which is 2t. So this 2 cancels with this half. So this implies that dy dt is equal to root 5t times t squared plus 1 to the minus 1/2. Now we have to show that this is equal to this if this is y. So we're going to plug this all in. So we know what y is, so this is going to be t times y, which is root 5 times t squared plus 1 to the 1/2 minus 3 plus 3t divided by t squared plus 1. Now if we simplify everything in the numerator, we can expand the brackets and group like terms. So we will get t times this expression, which is root 5t times t squared plus 1 to the 1/2. T times minus 3 is minus 3t. Minus 3t plus 3, that cancels out. This is divided by t squared plus 1 to the 1. T squared plus 1 to the half divided by t squared plus 1 to the 1 is t squared plus 1 to the minus half. So this is root 5t times t squared plus 1 to the minus 1/2. And this, we know, is equal to dy dt. So therefore this checks out. So we found the solution over on the right side. We first found the general solution. We then found the specific solution. Once we found that solution, we didn't stop there. We then came back to the initial equation. We differentiated the specific solution we found. We plugged that into the first order differential equation to confirm that that was in fact the solution. This is a very, very useful thing to get in the habit of doing once you're at, say, the first year university maths level. Once you're doing higher level maths, you need to not only be able to do the maths, you need to be able to confirm that the maths is correct. Right? Otherwise you will lose a lot of marks. If you make a small mistake in a very long question and it ends up being wrong because your mistake sort of ruined everything else, if you have a really harsh marker, you will lose a lot of marks. Right? They will just say they didn't bother checking, they don't really know what they're doing, and they'll take a lot of marks away from you. So check wherever possible. It's a really good habit to be in.